Let us come back to quadrature carrier multiplexing. As you can see in the transmitter diagram that we have on the screen, there are two signals to be transmitted, M1T and M2T. These are the two modulating signals. In any other conventional AM system, to transmit two modulating signals, we will require two different carrier signals. When I say two different carrier signals, we will require two carrier signals with two different frequencies. But I can achieve the transmission of two modulating signals using one single carrier frequency also. All we have to do is take the original carrier, which in this case is AC cos 2 pi fct. So the original carrier is in the cosine form. Along with the first modulating signal M1T, it is given to a product modulator. Let me quickly remind you, this product modulator is nothing but the balance modulator, which will multiply the two signals. So if I write down output of the first product modulator, let me call it Y1T. Y1T is going to be nothing but M1T multiplied with AC cos 2 pi fct, where AC is the peak amplitude of the carrier signal. So what you observe here is we get double sideband suppressed carrier form for the first signal M1T. So let me also at the same time express the frequency components of the signal. Let's say if M1T consists of frequencies of 0 to FM1, in that case this signal Y1T will have the frequencies Fc minus FM1 to Fc plus FM1. So that's my two sidebands, double sideband suppressed carrier signal. There is no carrier here because we are using balance modulator. Similarly, look at the second product modulator which we have, which is also nothing but the circuit of balance modulator. Before we give the carrier to the second modulator, you can see the carrier is passed through a 90-degree phase shifter block. Because of this, the output of the phase shifter or the input to the second product modulator will be nothing but sine form of the same carrier frequency. So the frequency remains same, but the signal that we use as a carrier to the second modulator is the 90-degree phase shifted version of the cosine function. So if I write down output of the second product modulator Y2T, it will be M2T into AC, this time sine 2 pi fct. So like the previous signal, this is also the double sideband suppressed version. This time it will contain the second information signal, which is M2T. So let us say that M2T contains frequencies from 0 to FM2. In that case, Y2T will contain frequencies from Fc minus FM2 to Fc plus FM2. Now please remember that both M1 and M2 are ultimately the modulating signals. In amplitude modulation system, they can be the audio signals. The audio signals consisting of audio frequencies in the range 20 Hz to 20 kHz. So it may happen that FM1 and FM2 is same for the two modulating signal. It may perfectly happen. In this case, if you observe the frequency spectrum from Fc minus FM1 to Fc plus FM1 and the second frequency spectrum from Fc minus FM2 to Fc plus FM2, both will coincide with each other, both will overlap with each other. Now this simply indicates that there will be overlapping of the two modulated signals, and if this overlapping or the mixture of the two modulated signals cannot be separated out on the receiver side, then the demodulation of M1 and M2 will not be possible. Now it is very obvious that the reason we are discussing this as an amplitude modulation system means there is some way to separate out the two signals. So let us discuss that in the form of the receiver. So this is a transmitter of quadrature carrier multiplexing. My final multiplex signal S of t will be nothing but sum of the two signals Y1T plus Y2T, as we are using added block at the output. So I'm adding the two modulated signal and transmitting it to the receiver side. Let us see when receiver receives the sum of the two signals, how it will extract M1T and M2T from the common received signal.